Okay, section 8.3 is trigonometry. Now you're going to need your calculator for this, so please grab your graphing calculator. If you don't have one handy, do the best you can by just paying attention, but in class we'll go over the calculator use again. If you don't have a graphing calculator, that would be a TI-83 or TI-84. You need to get one pretty quickly. So we need either a TI-83 or TI-84. Okay? All right, so let's get going. We're going to look at something today called trigonometric ratios. Trigonometric ratios. We've learned that similar triangles have similar ratios for corresponding sides. Therefore, like angles have like ratios. So if I have two similar triangles, okay, the ratio, whatever this angle is, we're assuming that these are similar, the ratio of side A to B is the same as the ratio of side C to D, and this angle measure has to be the same because they are similar triangles. So similar triangles have similar ratios for their corresponding sides, therefore like angles have like ratios. We're going to use that for the ratios of the sides of a right triangle. And when we talk about the ratios of particular sides of a right triangle, we assign names to the ratios. So we use special names for these ratios in a right triangle. So let's see what those are. So there's our right triangle. It's common practice to use capital letters for the angle measures, and the side opposite to each angle uses the same lowercase letter. And we always use C for the hypotenuse. That's how we get our A squared plus B squared equals C squared. So angle A is one of the two acute angles. It is opposite side A. Angle B, sorry, that's kind of off the screen a little bit, is side B, and angle C is opposite the hypotenuse or side C. So here's our first trig ratio. The sine. The sine of angle A, that's the name that we give to the ratio for the length of the opposite leg, simplified by O for opposite, over the length of the hypotenuse, which again we use H for. Now in this diagram, it would be A over C, opposite over the hypotenuse. And this would be the same as true for sine of angle B or angle, well actually just A or B, because we cannot use the right angle for this particular process that we're doing. So the sine of angle B would be its opposite over the hypotenuse, or B over C. The cosine, again, we're looking at angle A for the purposes of this slide, is the length of the adjacent leg, the leg next to angle A, over the hypotenuse. So for angle A, it would be B over C. The cosine of angle B in this case would be its adjacent, A over C. The last trig ratio we're going to look at is called tangent. So these are our three names: sine, cosine, and tangent. And the tangent is the length of the opposite leg, in this case A, over the adjacent leg, in this case B. So the sine of any angle is its opposite over hypotenuse. The cosine of any angle is its adjacent over the hypotenuse. And the tangent of any angle is the opposite over the adjacent. So these need to be memorized, and I will give you in class a little kind of an easy way to remember sine, cosine, and tangent. But for right now, the sine of any angle is its opposite side over the hypotenuse side. It's a ratio. The cosine of any angle is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Okay, so how are we going to use this? We're going to write a trigonometric ratio for the sine, cosine, and tangent of angle P. So the sine of angle P is its opposite over its hypotenuse. Opposite to P is 15. The hypotenuse is 17. So the sine of angle P is 15 over 17. The cosine of P, I'm going to write it this way now. The cosine is the adjacent over the hypotenuse. So therefore the cosine of P is 8 over 17. Notice that I've also abbreviated sine and cosine. These are the abbreviations that we use for sine and cosine. Tan of P is the abbreviation for tangent. It's the opposite over the adjacent. So for P, the opposite is 15, the adjacent is 8. It's 15 over 8. Okay? So sine, opposite over hypotenuse, cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. Now, no matter how big or small I make this triangle, if it is similar, angle P is always the same. So there is a specific angle measure that goes with these ratios, and we can get that from our calculator. And we'll look at that in just a minute. The first thing we're going to do with our calculator is use a calculator to find a side length of a right triangle, as long as you know one angle and the other side length. So I have an angle of 54 degrees. I am looking for the opposite side, and I know the hypotenuse. So the trigonometric ratio that deals with opposite and hypotenuse is our sine. The sine of angle, the sine of 54 degrees in this case, is going to be the opposite W over the hypotenuse, 17. Sine of any angle, we'll use just an X for a general, is the opposite over the hypotenuse. Okay? So since sine is opposite over hypotenuse, and I'm looking for the opposite, and I have the hypotenuse, I'm going to use sine. Sine of 54 degrees is W over 17. To solve for W, I would multiply both sides by 17. And this is where I need my calculator. So if you have your calculator handy, turn it on, and you'll notice that above, 2 keys above the 7 is the word sine, S-I-N. If you plug in 17, then push the sine button and put in your 54 degrees, you should get, you should get 13.75, and then there's some other numbers as well, but 2 decimal places is enough. If you get something different, look at your mode key, which is up near the top of that same column, and go down to the 3rd line, and you have a choice of radian or degree. Make sure that your calculator is set on degrees, and then go back and try it again. So 17 is getting plugged in. We hit the sine key and then put in our 54 degrees. Since sine of 54 has the same number no matter what size my triangle is, as long as there's a 54 degree angle, I can use the trig ratios to find a missing side. So let's try 2 more. And I want you to go ahead and first of all find angle X. So let's look at that. I'm using angle 23 degrees. I have the adjacent side and I'm looking for the hypotenuse. So the cosine of any angle is the adjacent over the hypotenuse. So I'm going to use the cosine of 23 is the adjacent 21 over my unknown x. Now to solve this one, since the variable is in the denominator, I'm going to have to multiply both sides by x and then divide by the cosine of 23. That cosine of 23 represents one number. So I'm going to plug into my calculator 21 divided by, push the cosine button right next to the sign, type in 23, and I get 22.81, and then there's a few more numbers as well. What about to find y here? Y is opposite. So I have opposite and adjacent. That's the tangent. Tangent of x equals opposite over adjacent. Since my variable's on top, I only have to do one step to isolate. Whoops, I shouldn't have x, I should have 23 degrees because I know my angle measure. So 21 times the tangent of 23, and that is going to be y equals 8.91. And you can always go back and look. Remember, the smallest angle has the smallest side opposite. So 8.91 makes sense. X should be the longest side because it's the hypotenuse. Okay, try this green triangle on your own. Find X first and then Y, and then come on back. Okay, X is the hypotenuse. I know 45 degrees and I have the opposite. So I'm going to use the sine of 45 degrees equals the opposite over x. Again, I'm going to have to do two steps to isolate the x. So x equals 3 divided by the sine of 45 degrees. And if you use your calculator for that, you should get 4.2426. How about y? Again, I've got the opposite. Now I'm looking for the adjacent side, the next two sides. So the tangent of 45 degrees equals opposite over adjacent. So multiplying both sides by y and then dividing by the tangent of 45. 3 divided by the tangent of 45 is 3. Now remember that we talked about 45 degrees as being a special triangle and having sides 1, 1, or s root 2. So here's my side. This side is the same. X should be 3 root 2. And if we plug that into our calculators, we do get our 4.2426. So we could have done this one without a calculator because we know the ratio of the sides of a 45-degree triangle. It's one of our special triangles. So let's look at this one and see if we can find a missing angle this time. So given two side lengths, we can also find an angle measure using trig inverses. Well, first of all, angle C is here, and I have opposite and hypotenuse. So opposite over hypotenuse is the sine. The sine of angle C is 6 over 10. When I'm missing the angle, I'm going to use the second key that says sine inverse. So second, and then if you push sine, just above that it says sine inverse. And I'm going to plug in sine inverse of 6/10. And what this does is it gives me the degrees for angle C. So if I use the inverse key, I get the degrees, whereas when I use the regular key, I found the side length. We'll talk about this more in class, and we're going to do quite a bit of this in class before we get going. Okay, so special triangles. So we should be able to do this without a calculator. Again, we know that my special triangle is side root 2. So if this side is 2, that should be 2, and that should be 2 root 2. And that's how easy it is when we have one of our special triangles. But again, keep in mind, you've got to know those ratios for the sides of the special triangles. So we've got one more to look at. This one, I don't have an angle measure, but I do know that this side is half of the hypotenuse. And the triangle that we learned for that, where it was 1, 2, root 3, was my 30, 60. So this has to be 30. This has to be 60 because my ratio is 1 to 2. And this side has to be 5 root 3. And that's it. And we will do more of this in class, as I said.